I think it's 5:10 now. So have you guys think over it? Did you think over it? What is this static RAM and what is valid and what is write read enable and what is address clock and reset and ready and R data and W data? Did you think over it? This is the static RAM we'll be going to discuss today. So it is like a volatile. I think we know everybody can understand what is volatile and non-volatile, which is not permanent, it is volatile, right? So here address is the input. By looking at the diagram, you just think over it, the direction of your arrows. So this is input. Now address is the input pin and valid and R data. Sorry, write read enable is the input and W data is the input and R data is the output, right? And this is also ready is also a output here. And then a clock and reset are the inputs here. This is the RAM will be going to implement the design. Okay. Now let me share the notes. Everyone is clear on it? Can I get reply? Yeah. So static RAM we are discussing. So it is volatile memory. So what are the signals of the memory design? The DUT we are creating this one. We are implementing the design and the test as a static RAM. That is SRAM. So now signals of the memory signal. Now just can you tell me that meeting is going on? Tell me the inputs and outputs. What are the inputs we discussed? Address is the input. So can I define it as a I after the signal name? Yeah. Clock and reset. Clock and reset are common for all designs. Clock and reset, address I, valid I, write read enable, write read I. These are the inputs. What are the output we have seen in the diagram? Radio and the R data. So these are the input and output signals. So we are designing the RAM okay. Voice is not clear. All of you?
It's clear.
It's audible, ma'am.
Yeah, it's okay.
Yeah, designing the RAM. So we are designing the RAM here. So 1 KB memory. 1 KB memory. Whose width is 8 bit. So how can we calculate what is the depth? We need to find it out. So how can we calculate the depth? So any given memory, whatever the memory they are giving, you just convert into the bit. How to convert the 1 KB memory into bits? Convert the given memory into bits. Tell me. 1 KB memory. How many bits? 1 KB memory is how many bits? 1024, right? 1024 bits. Yeah, very good. So if I want to design 4 KB memory, if I want to create the 4 KB memory, which means that we have to multiply 1 KB 4 into 1 KB into, this is the byte actually. 1024 byte. Yeah, it's not going back. 1024 byte. So 1 byte equal to 8 bits. 8 bits. If I want to convert, for example, if it is a 4 KB memory, if I want to convert into bits, what I have to do? 4 into 1024 into 8 bits, right? Yeah. 4096 into 8, correct. So 4 into 1024 into 8. Whose width is, for example, 16. The size formula of the memory, width into depth. So if you want to find it out, the depth, I can write size by width, right? What is the size we converted above? How can we get this one? Depth. Depth equal to size you already converted into bits. 1024 into 8 divided by 16. Can you calculate and tell me the result? 1024 into 2. 4 4 is 16, 4 2 is 8. 1024 into 8. 1024 into 2. 2048. This is the depth. So like how we have to calculate. So now let us implement the 1 KB memory. Okay, we are designing 1 KB memory. We are developing the code for that one. So module name is the memory. We are designing the static RAM. So clock, we are declaring all the inputs and outputs in the port list. Clock reset address underscore I, comma, W data underscore I, valid is the input, write rate enable I. So what about write read enable? Write read enable is deciding when I am writing data into the memory or reading data from the memory. It is a control input. Control input is the write rate enable input. Write read enable line, which means that it is telling that whether we are writing data into the memory when write read enable pin is enabled. Enable means what? It is high, right? Write read I equal to 1. When I set to my write read enable pin is 1, that is it is indicating that we can able to write data into the memory. If the same way if it is 0, pasting is not working. So it is if write read enable equal to 0. If it is set to 0, which means that we are reading data from the memory. Reading data from the memory. And what about valid I and radio? When master is trying to give the information to the slave also should give the response to it, like acknowledgement. Okay, I am also ready to take that information. So these are the handshaking signals. Handshaking signals. What are those? When valid and ready are set to 1. Valid and ready are set to 1. We can do both write and read transactions. We can do both write and read transactions. Okay. So when I set to my write read enable, for both write and read, we are setting one only. The valid and ready should be one for the both write and read. But whereas my control pin of the write read enable must be one for the write logic, 0 for the read logic. Okay. Write read I valid and R data O. So end middle. So now we will declare the parameters again and again. What is the requirement? Why do we require the parameters here? So when you design your design, when you implement a design using the parameters, in future if you want to increase the memory, you no need to go and change your code, right? That is the advantage of the parameters. You can just go and change the parameter values. For example, here size is 1024. 1024, which is 1 KB byte, 1 KB memory. So if I want to change in future, I want to have the 4 byte memory. So 4 KB. And you can change, go and simply change your size of the parameter, right? That is the parameter width. Yeah, we can modify the size in future without touching the design. So width, it is like 8-bit. Parameter, I can copy above. Parameter depth equal to 16. And parameter address width. Address width, there is a system task one formula is there for the log base 2. So $C log 2, you're passing the depth inside it. This will convert you into the 2 power n value. 2 power n value. The tool will calculate whatever the depth you are passing. Can you just convert into the 16 into 2 power n value? What can be the 2 power n value for the 16? I pass the depth parameter using the $C log. $C log is converting into the logarithm formula. So 16, how can we write into the 2 power n value? 2 power 2 is how much?
4.
2 power 3, 8, 2 power 4, 16, right? So that automatically will convert into this action will be done by the tool. How it will convert logarithm formula? Log 2 base 2. Log 2 base 2. So here we are writing the 2 power 4. So 4 we are writing here. 2 power 4. 4 will come here, which means that, okay, it will convert like that. No need to explain about all those things, but still. Log 2 base 2. So now parameters declaration is completed. Now I want to declare the inputs and outputs. What are the inputs? Log. Scalar inputs are, we will write in single line. This is scalar pin, either 0 or 1. Preset is also either 0 or 1. Valid and ready also we are indicating for writing purpose, we are taking single bit, that is 1. Reading purpose, we are taking the 0. So I can write, this is also scalar type, right? Valid and ready also scalar. And only the vector form we can write R data and W data. So you can declare all the scalars and vectors in single line. I mean, scalars we can write in a single line. So valid underscore I, write rate underscore I. So now input address width. Address underscore width, which is address underscore I. Input width minus 1 down to 0. This is the memory declaration. I mean, This is the W data underscore I. And then output. Output must be declared as a reg type. We have learned yesterday using the behavioral modeling style. So output R data I want to declare. So width -1 down to 0. R data underscore O. And the output reg ready. O. So all the inputs and outputs are completed. Now I have to declare the memory size. Memory size we are writing using the parameters only. Reg width is in the form of vector dimension, the number of bits it is taking. How much width we have declared here? 8 bits, right? So 8 it is taking. So width is in the form of the the data bits are in the form of the width here. So width we are taking it in the dimension of here, bit size, and the memory size is an array. This is the depth. The locations will be increment from the 0 to 15. That is 16. Okay. This is width is in the form of vectors and array size is in the form of the depth. That is what I wanted to tell you. So width -1 down to 0. Memo depth -1 down to 0. So this is called memory storage. We declared in the parameter way. We declared one integer I. So now I have to write the logic. Write logic. First we will implement the reset logic. Then write logic. Write logic. So always procedural block we are using at every positive edge of the clock. Passage clock I. So begin and end. Inside. If reset is high, we are setting reset pin is high, we have to make it circuit become 0. Okay, otherwise it will catch the memory values, like unknown values it will catch. That is the reason every design, whenever you are making, you have to make it all the edges 0. You have to apply 0 to the all the edges. Whatever the edges from your design file, you just have to apply to that 0. You have to apply. Why we are doing this one? Because system has to come into the known state. Somewhere I can't start in between, right? If I want to design something, I can't start from the center of the point. I just have to bring my system into known state. Then only I can start up the system, whatever the logic I want to write it. So every time we have to follow this one. Any flip-flop, you just have to reset. Any design, you have to reset first of all. If reset is applied, make all the edges 0. So what are the edges here from the design? R data and ready are the edges. And this is also, memory is also we declared in the form of the reg, right? Radio equal to 0. R data underscore equal to. We applied the 0 to the ready and data. But can I declare directly? I can assign the value to the memory. These are the vector form, right? 3-bit, how many bits vector? For example, what is the depth you have taken? 16-bit vector. But how can I declare each and every location? I can't assign at a time, right? Memory cannot be assigned a value directly. Like however you are declaring the ready and R data, we just have to location wise we have to assign value, index wise. You got that point or not? If I want to initialize the 0 to the memory equal to 0. I can't do like this because it has the address locations. Address locations will be incremented by pointer wise, one after another, one after another. It is not a vector to assign at a time. If it is a vector, I can assign at a time 0 to all the index values. But here it is the address is in the form of the depth, like location wise. So it has a location. So that is the reason you have to assign value with the index wise. This is correct. Okay. Mem of I equal to 0. So index wise should assign any value. If you want to assign particular index wise only you have to assign. So for that we have to write the for loop there. So how can we write this one? For loop I equal to 0 and less than that I plus plus. I plus plus incrementing operator is not supported in the Verilog. You have to write I equal to I plus 1. But I plus plus it is possible in the SystemVerilog. So now I can apply mem of I equal to 0. If not reset. Here it is up to condition where we have written up to this condition. It is a if reset is applied up to this end. After that else part we have to write it, right? Else begin and end. If condition. Write underscore read underscore equal to 1. If write read enable is 1, begin and end. How many conditions we need to check before writing data into the memory? We should be check the write enable control. At the same time, we have to check the valid and ready also should be 1. Then only we can able to write data into the memory. So we already have written one condition for the write read I. And one more if condition we are writing for valid underscore I equal to 1. Then begin and then we are checking the ready should become 1. Ready underscore equal to 0. We check the handshaking. Now every possibility is done. So we should have to check the write read enable 1 is the right logic. Write read enable is this is also 1. I have written 1. So handshaking is also done. Now I can write the data into the memory. Mem of address underscore I equal to W data. I'm putting the data into the memory. So now writing data into memory after checking all the conditions. This condition up to where PO. In the else begin only I have to write it read logic as well, right? Else part. Else begin, what is that? Begin and end. Else begin and end. Our data. We are reading from the memory. Address. So we are reading in the else part. In the else part means all these conditions are not up. Like if else condition, if write read enable is 1, so it fails. No, it has to come here and it has to read data from it. So reading data from memory. After that, I just wanted to break the handshaking. After reading everything, I should break the handshaking, right? Handshaking is okay. If it is set to 1, both write and read transactions can happen. I have to de-enable means I have to set to 0 that. So it is handshaking is flipped. Now design logic is completed. We implemented the design for the memory. We have to develop the test bench for it. Mem underscore tp dot. First, I need to include the design file. tp.a module dot. So end module. So I have to copy all the inputs and outputs from the design parameters, including the parameters, how many lines would be there. So up to the integer I, it is like around 14 lines, which means that I can copy 13 lines, 13 by 13 by He is not working. Okay, let me type it again. So module dot. So parameter size 1024. Why do we require again parameters here? If you want to do the overriding of my test bench, whatever the design parameters, I can override during the test bench only. During the simulation time only, we can change the values without touching the design parameters. I can also change during the runtime only. I can change it. I don't want to go and change the values parameters of the design. I can also change here only. That is called parameter overriding. To implement parameter overriding, again you have to declare whatever the design is having all the parameters. You have to declare in the db.a. Okay. In the test bench also you have to declare. Parameter that is 16. Parameter address. So convert all the inputs and outputs. Manually, I will copy instead of typing. The command is not working. So manually, let me copy and then later we can change all the things accordingly. So change all the inputs as a reg type. Output must be declared as a wire type, right? So I have to convert that into %s. So input convert into reg global character. So S. Now I want to change the output as a wire type. All the outputs will have to declare as a wire. So wire ready. Ready is semicolon is missing in the design as well. So integer I. Integer I. So now what is the next step? As of now, we implemented the behavioral style modeling and data flow modeling. We implemented the test benches, right? Yesterday we have seen the 3 designs or 4 designs we implemented. We developed the design as well as the test bench. So what is the next step? After changing all the inputs as a reg type and all the outputs as a wire type, what is the next step we have to do? DUT instantiation, right? Stepwise you can remember like that. So DUT instantiation. What is the DUT instantiation? How we can do? So module name memory DUT. If I want to do the parameter overriding, so I have to take hash. What are the parameters declared in the design and the as well as in the test bench? All the parameters take it as a connection by name. So width and the depth of 10. Then address width. Address width and the size. 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 So all the parameters are done. So now I have to do the DUT instantiation. So clock underscore I, connection by position, address underscore I, W data underscore I, valid underscore I, write read enable, data underscore O, ready. So all things are done. DUT instantiation is done. Now I have to generate the clock. How to generate the clock in the processor block of the initial, begin, and end. So initially is designed for the Testbench. Always we have to use for the design purpose. Okay. Initial block, initial processor block you have to use for the Testbench, and always you have to use for the design. So now I want to generate the clock. So how can we, because I have the clock and reset in the design, right? I need to generate. So initially make it clock as high or else 0. If you give 1, it will start from the positive edge of the clock. If you have given upright the 0, it will start from the negative. Okay. So clock equal to 0. Forever code we are using, forever #5 clock underscore I equal to negative edge of the clock underscore n. What it is telling that here the TP is 10. TP is 10 means what? 5 units of time clock is high, 5 units of time clock is low. Clock all the time need to toggle, right? 5 units high, 5 units low. So that is the reason total time period is not the TP, that is I was meant by TP, time period. TP is 10 seconds. Okay. So now initial, begin, and end. So I want to generate the reset. First I can write reset underscore I equal to set to 1, hold it for some time, 10 units of time, reset equal to 0. I apply the reset and release the reset and hold it for the 10 units of time. We know why do we have to generate the reset? We discussed in the design part. So whenever you are doing, when reset is applied, all the edges, you have to apply all the edges 0. So now let us implement the task for the write logic. This is the write logic. We are writing. So task. I hope everybody know about the task and functions, right? Task name, insert braces. Task can allows both the inputs and outputs parameters. But as whereas in the function cannot allow, in the Verilog especially, Verilog functions cannot allow the outputs in the argument list. Okay. So task name. So memory write. Memory write. So input. Address with the -1 down to 0. Start location. The argument we are giving for the input is a start location, and the second input I'm passing it as address bit down to 0. This is the number of locations. How many locations I want to write? So end task. So Verilog task and function, we have to write begin and end. So it is not it is not required in the SystemVerilog, but here we have to write begin and end. So for loop I'm writing I equal to, instead of 0 we are writing the argument as a start underscore location. Start underscore location. I less than start location plus number of locations. I equal to I plus 1. So begin and end. So at every positive edge of the block, you have to do this action. So every passage of the block I, you're applying this one. Address underscore I equal to I. You're assigning the value I, whatever the iteration you have done in the above, that you are assigning to that every location, right? Start location, it is indicating in the, you have written the condition above in the for loop, right? So address, you're assigning it. So then before writing data, we have to check the write read enable should be the, but read logic write read enable should be 1. So valid should be 1. Valid I should be the 1. And then we have to randomize the duplicate. I'm applying the random inputs to the duplicator. And then we have to wait for the ready should become 1. The handshaking should happen, right? So, and then I have to call the reset after writing and read logic. After writing into the memory, after reading from the memory, I have to call the reset here. Call the reset. Again, we have to call reset whenever I have updated the reset one. Here I have to call the reset. Later we will go. So that we can also implement the task for it. So task is done. The write task is done. We have to implement the same code I can copy for the read logic. Some changes we can make it in the code, but still we are writing. Memory, read, so input, address put -1 down to 0, start location, input, address put down to 0, number of locations, and task. So now begin and should be there. But I equal to start location, I less than start location plus number of locations. I equal to I plus 1. So begin and end. So I positive edge of the block. So address is assigned to the I. So write read, what is that? Before write read, I can write, write read. What is write read should be for the read logic as per the discussion. 0, right? Valid underscore I must be. For both write and read, valid and handshaking should happen for the both writes and reads. Right? Handshaking, valid 1, ready 1. So you have to wait, ready should become 1. Again, you can apply the reset. Call the reset. Posage clock I. Call the reset task. Instead of writing like I want to all the registers, what are the registers from the test bench? You guys can look it over the code and tell me what are the reg variables from the test bench. Clock and reset. Apart from the clock and reset, because we already generated the clock and reset. Apart from the clock and reset, how many registers are there in the test bench? All the inputs, right? Whatever the inputs are there, those are the registers in this design, right? So valid, write, read, address, and update. So all these have to apply 0. Instead of writing again and again, the piece of code, once we have to implement, what is the use of task and functions? We can implement one code and we can call that task wherever the piece of code you want in it, right? Again and again, you can call that piece of code. That is what we are doing it here. So now we are implementing the task for the reset inputs. Reset inputs. End task. What are the inputs? So begin and should be there. Begin and end. Address is the input. Address equal to 0. Write underscore read underscore I should be the 0. Valid underscore I equal to 0. W8 underscore I equal to. I upload all the inputs. So I have to call this task. This piece of code, see, these 4-5 lines I have to write here when I'm reading from the memory. And here I have to read it again. 4 lines of code. Instead, we are reducing the code length. So by implementing the task, this piece of code, wherever I want in my code, if I want to call the reset logic, I can call it here. What is the task name here? How can I call it? So reset underscore inputs. And here also we can call it reset underscore inputs. And where I need it, one more place here. When I upload the 0. When I upload the reset equal to 1. Reset underscore inputs. The particular piece of code, we are calling it everywhere we want in it. So now we completed this one. What is the use of this one? Now we can develop the test cases for it. So for that, what I have to do, in the Verilog, there is a system task and function. It can be the system task and function. $value, dollar plus args. $value, dollar plus arg. It can act like a system task or function. System task or function. So it allows user to read the arguments during the elaboration. So it allows the arguments from the elaboration time. Okay. What does that mean? We will discuss when we are implementing in the code. So for that, I have to implement the test cases, I have to declare the vectors, reg vectors, right? We don't have the string in the Verilog, so we have to declare them as a reg vectors. 30 characters into 8. So each and every character is holding the 8 bytes of data. So that is the reason 30 into 8 we are multiplying. 30 into 8 I can't leave like this. Okay, 30 into 8 minus 1 down to 0. This is the Verilog style. If it is a system Verilog, there is a string data type. I can directly declare the string here. But Verilog doesn't support the string type. Okay, that is the reason we have to go with the reg vectors. 30 down, 30 into 8 minus 1 down to 0. Now I can write $value, dollar plus args as a test name, printing in the string format. So test name. So I want to develop the test cases now. Case of test name. Case and case. Inside we should develop the test cases. Memory, full, write and read. Full write and read. How can we write data into the memory? Whatever the task we implemented below. We already implemented one task here. I can call the task here. This action should come here, right? So I implemented the memory write rate. So I no need to write all this logic using the for loop. If without task, I need to write this logic, complete logic here. So instead of doing that one, we implemented one piece of code and we are calling this task here. So how can we tell that whether we are writing full writes and reads? We can do like this. So memory, the task name is memory underscore write. So 0, depth. So 0, depth means the first parameter is indicating the start of the location. We are starting from this, and what is this one? Number of locations. This depth parameter, it is indicating number of locations. So 0 to number of locations, we passed directly depth. Depth, how much it is we have declared in the memory. So 16 locations, right? 0 to 15 it will take. Memory underscore read. 0, depth. So now another test case. Begin and should be there for the test cases in the Verilog. It's not required in the SystemVerilog, but here everything we have to write, any task or cases, anything you are writing, begin and should be there. So next test case, first quarter of the memory we will see. First quarter of the memory. Begin and end. So first quarter of the memory, how we will write it? Memory, we are writing first to 0th location. Let me draw and show you that one. See here, this is the memory. Okay, this is 0th location. 0, 1, and so on up to here what? At least let me do 4 locations first. This is 0. This is 1. This is 2. This is 3. From here to here, first quarter or not? This is the first quarter of the memory, right? This is the first quarter. And what will be the next location? 4, 5, and 6, and 7. Up to 7 is the second quarter. Isn't that all of you? Can I get an answer from you? 0 to 4, 4 to 7 is the second quarter. Second quarter of the memory. And tell me from after the, what are the locations we have to for the third location and fourth locations? This is upper location is 0 to 15 we are writing. Can you just post your answers in the chat box? I declared here 0 to 3 and 4 to 7 are the first and second quarter of the memory. What can be the third and fourth quarters of the, can you write the values in the chat box? Quarter means 4, right? 4 values you have to take it. So 8 to 11. Okay. 8 to 11. And then 12 to 15, right? Yeah. Now let us implement in the code whatever we are writing. So how can I get it first quarter of the memory? First location, starting of the index is 0. And I can pass it depth rate. Depth by 4 means what? 16. My depth we declared in the test bench as a 16. 16 by 4 is 4 4 is 16. Is it correct? So memory, read locations. I'm reading same locations like 0 to, again, depth by 4. This first quarter of the memory is done. Then the next second quarter of the memory. begin and end. So how can I get it from the, I need to start my, this is the start location. There is no issue, no need of changing any values. Here I have started, here how many values we are getting? 0 to 0, 1, 2, 3 we are getting, right? So from here I have to start from where? Fourth location upwards. How can I start that one logic? Memory underscore write. How can I pass the parameters? I need to start the location from the 4. Can I write depth by 4? Again, depth by 4. Depth by 4, depth by 4. This is the start location, which means that depth I passed a parameter 16 by 4 as a 4 here, which means that start location is 4 and the number of locations are also 4. Are you getting? Read. Same. Depth by 4. Now you have to think over it. Next value. Next test case. What can be the next test case? Third quarter of the memory. Third quarter of the memory. Can you guys guess this one? How can I start? Location. Start of the address. This is the starting parameter, right? This is the starting parameter. These are the number of locations. Depth by 2, if I write it, will it start from where? Okay. So 4, 5, 7, right? I can start depth by 2. Very good. Memory, right? Depth by 2, comma. This is depth by 4 only because I want to read only 4 values. Memory underscore read depth by 2, comma, depth by 4. This one. Next memory, last quarter of the memory, fourth quarter of the memory. How can I write it? Think over it. Begin and end. Memory underscore write memory underscore read. How can I write? Start location. From where we ended here, 8 to 8, 9, 10, 11. So I need to start from the 12th. So I can write 3 into depth by 3 into depth by 4. Wait a minute. 3 into, yeah, depth by 4, correct. Depth by 4, comma, depth by 4. What it is indicating here, 3 into depth by 4 means what? Depth by 4 is 16. Is it correct? 4 we are getting. Depth by 4 is the 4 we are getting. 4 3s are 12. We are starting from the 12th locations, right? So memory read as well, same. 3 into depth by 4, comma, depth by 4. Now, this is the test cases we implemented for the all the quarter of the memories. Yeah. First and second and third and fourth. Yeah. So now we implemented this. So to run this code, SPL run.to Verilog tb.v vsim tv. So add wave hyphen position insert point. To see the waveform, we have to pass this command. So add wave hyphen position insert point sim. So tv dut start run hyphen on. But we have to read the user provided arguments, right? We implemented the test cases and we are using this $value plus R to read the commands from here, right? The arguments should read from the elaboration. So we have to pass it the test name here plus test name equal to whatever the test case you want to run. That test case you have to pass it here. So memory full write. If you want to see the full write and full read, you have to pass the test case name here. So full write memory full write full read. So if you want to see the another test case, sometimes it may not give the proper values at the time. You can comment all the test cases. I'm sorry. Whenever you are working on the single test case, you just comment all the remaining test cases as well. You can comment the below code by having the multiple commented codes, right? You can comment like this. Whenever you are working on the third quarter of the memory, you can comment other test cases. Sometimes it may not read it. So sometimes it will allow you to, without blocking also, you can get the result. This is about the project. Any doubts as of now? Do you guys have any doubts?
Can you show me waveform, ma'am?
Yeah, we will show it. Any other doubts are there? Let me.
And it is possible to upload this video. Again, I will see. I will watch.
Yeah, we will provide the recorded sessions later.
Wait a minute. Let me open the resume. Yeah, I'm not speaking anything. I'm just opening the models. You have to enter all the time with cd space. So here it is the waveform. You just convert into unsigned number. Control A, right shift, unsigned. Now we can able to read the value. See, I will unlock this one. See here at the 0th index, we can able to see write read enable is high. So when the write read enable is 1, where my write read enable is 1 at this cursor, right? So from here onwards, I'm able to write data and read data as well. So writing data into the memory. So 0th location, we have this address. How much it is? 348826. And the next location, 32 location number. So that is, they have written here how much it is. Tool is generated 41284. So 41284. Same thing, you have to read it. So where is the ready read data? Write read enable is 0. Here it is the write read enable is 1 means here we are writing into the memory. So at the time reset should be low, right? Here reset is low only. See, you can see the value here. Reset is low. Then only we can able to write. If reset is applied, all things should come into 0. The values we are getting the 0 here. But here when reset is 0, then we can able to do the whatever the write logic and read logic. That is concept, right? We have learned in the notes. And we have to check for the read values. If you can observe here, it is the write read enable is 0. When write read enable is 0 here, you can look at my cursor. So we can able to write the data. Whatever the 0th location we are writing, 34826, and 32 location it is taking 41284. So we are writing full writes and full reads. Again, if you want to check any other test cases, you have to pass it over there. You can check like that is homework for you. Okay, you just have to implement, delete the test cases, whatever the test case we have written. You comment other test cases when you just pass the test case name. The first quarter and second quarter, that is homework for you. We already implemented, just pass it as an argument. Any doubts as of now? Online? So whatever we are writing into the memory, same thing we have to read from the memory. At the time, you have to check the W data. At my 0th location, some value is there. Are we reading the 0th location with the same value? Are we reading with the second location from the same value? You just have to check like that. Yeah, that's it. And I think we have to take the introduction of the SystemVerilog, right? We'll get into that one. So why do we need the system Verilog? Already we discussed everything in the Verilog, right? There is the 4-state and 2-state variables are there. So these all the values, state variables only for the simulation purpose that we have learned in the introduction of the Verilog. So what are the state variables are there? 0, 1, X and Z, right? Unknown and high impedance. So logic 1, logic 0. So for that is the reason that these are the values. Can you please be
Hello, ma'am. Can you unmute yourself?
oh, sorry. Is it audible now?
Yeah, ma'am.
Yes, ma'am.
Okay, so we already discussed about the Verilog state variables, right? Verilog is supported the 4-state variables. Why do we require the 4-state variables? What are the 4-state variables that we have learned in the introduction of the Verilog? 0, logic 0, logic 1, unknown and high impedance, right? All these variables only for the simulation purpose, okay, not for the design purpose. Only for simulation means there are 4-state variables. That is the reason simulation is taking more time. So that is the reason we chose the system Verilog and we adapted the OOPS concepts over there. And we are adapting that is design verification is very easy implementation in the system Verilog because of the OOPS concepts. We can end of the day again you have to convert all these high level languages into the low level languages only. Gate level netlist only you are converting. But the verification is easy because of the 2-state variables and the OOPS concepts. We are bringing some constructs and OOPS concepts we are getting from the other foreign level languages. Okay. So, and here we are reducing the simulation time in the system Verilog. That is the reason we are switching. And one more thing, the medium and lower level design only possible in the Verilog. That is the reason we are switching to the system Verilog. So we can implement the complex designs by using the OOPS concepts and some more other constructs are added in the system Verilog. So that is the reason we can able to choose the system Verilog comparatively. For smaller designs and all, we can go with the Verilog HVLs. And HVL is more advanced. And this is the Testbench architecture of the system Verilog. This is the top module. Inside the top module, we have the hierarchy as a ENV. Inside the environment, we have the agent. Inside the agent, we have the agent components, generator, BFL, monitor, and coverage. And we have the scoreboard outside of the, it should be the ENV. I can also draw here. So why we have to declare the scoreboard inside the ENV environment? So if I have only one agent, there is no issue of the scoreboard inside of it, okay, inside the ENV. If I have multiple agents, there is a difficulty to implement the scoreboard. Each and every agent should be having the different scoreboards. So we are increasing the code, right, complexity, as well as the code length also. That is the reason you can keep it outside of the agent if you keep it like inside the ENV environment. So that is all the components directly communicate with the scoreboard. Okay. This is the generator. It generates the transactions. Whatever the test we are here, we are giving the transactions. No? So as per the user provided the random inputs, we are just getting inside the generator. Generator is generating the transactions and driving to the BFL through the mailbox. These are the mailboxes in between. Here, this is one class, this is one class. Class to class communication should happen through the mailbox only. So here, mailbox is a constructor, is like a synchronization between the generator and BFL. So we can't directly communicate because this is working on different thread, this is working on different thread. So I can't directly communicate. It can generate easily and pass that, and it can't capture values at the same time. No, if it is there is a delay between those two. So there is a waiting period. That is the reason we are using the mailboxes here. Between the monitor and coverage, between here generator and BFM. Any class-to-class communication should happen through the, here also we should have mailbox. So any class-to-class communication should happen through the mailboxes only. And here in the top module, we have the DUT, design under test post, whichever the design you want to check, the design you have to take it. And this is the interface. Interface is like intermediator between the DUT and the test bench components. Why do we require the interface and DUT? DUTs are working on the static, right? What is static in nature? DUTs are static in nature. So we can't change their memory, whatever the size and whatever the address width, we can't change it. There is no changes. The memory should allocated at the compile time only. That is called static in nature. So these are the dynamic in nature. I can do anything during the runtime. I can change, I can shrink the memory, I can adjust the memory, anything I can do it during the runtime. So these are dynamic in nature. Memory is allocated during the runtime. Here memory is allocated at the variables memory, okay, compiled time only. So but this is the duties are static in nature. These are dynamic in nature. Testbench components are dynamic in nature. I can't do direct communication here. That is the reason we require the interface. And interface is doing the bulking of signals. Whatever the BFM is driving, getting from the generator and it is driving to the DUT to check it. So when it is driving to the DUT, all these components, all the signals, it is grouping together and passing to the DUT. And again, my monitor is getting from the DUT. Here we are getting the signal level transactions and it is converting into the object level transactions because these are dynamic in nature. Again, it is taking and putting inside the mailbox. My coverage, when I want to do the coverage, I'm collecting from the mailbox which is shared by the monitor. So we are collecting from that. And whatever the monitor values we are sending here in the scoreboard, we are comparing both the actual and expected value. What can be the actual value and expected? Actual means whatever generating after randomization, whatever the inputs, we are getting something output right here. We are comparing here using the if conditions and Q methods. We are comparing the data, write data and read data. We are comparing whether it is fast or not. We are checking in the scoreboard. That one we are getting from collecting from the DUT. So okay, whatever we are driving and actual are where we are getting whatever design is already provided. For example, we have learned in the Verilog, we are applying the $random values to the A, B, the half adder values. A, B are the inputs and you are passing the random inputs, right? I'm sorry. Applying the random inputs and generating output. And after getting that values you are comparing with the truth table, right? That truth table value should match with your whatever the tool has generated when you apply the random values. That is your design is fast. Similar way, your DUT is providing something, whatever we are driving and we are collecting from the monitor, comparing in the scoreboard, that we are checking whether design is working or not. We are concluding that. This is about the testbench architecture. Do you have any doubts here?
No, ma'am.
Okay. If no, we can back that. Any of the students have any doubt regarding
Ma'am, I
system
think there is some question in the chat box. Can you please look into it?
The screen is not visible to them. That is the reason I'm just keeping aside chat box. That is the reason I expanded it. If we change the parameter size 4 KB, then all the values change automatically. Yeah, we have done the parameter overriding. Even no need of changing. That experiment you can do after implementation of the code. Okay, Sandeep. So do changes in the test bench only because we already have done implemented our test bench using the hash, right? Parameter overriding, which is called C. This is called parameter overriding. This step is called parameter overriding. We have done here. So no need of without changing any design parameters, you can only override from here itself. Okay. Do that experiment from your side and check it. So change the width to something and 16 Depth you can take it as a 215 like that. Is that okay, everyone? Any other doubts are there?
No, ma'am.
Ma'am, yesterday I was simulating the off header and max for one,
Mm.
and whenever I use the random, it only gives one state like 1 0, either 0 1.
Can you, okay,
Not all
can
the
you
four
share?
states.
Yeah, can you share the screen? We can check it and let us know.
Ma'am, okay, wait a minute.
Are you sharing? Mohammed?
Mohammed, are you trying to share the screen?
Yes, ma'am, I have joined from my mobile, so now I am joining from the laptop.
It's okay, Mohammed. You can share the screen tomorrow. You keep it ready
Okay.
for tomorrow's session and you can verify it.
Okay, ma'am. Will the recording be provided for today's and yesterday's lecture?
Yeah, we'll upload the recorded session.
Okay, thank you.
Hello, ma'am.
Yeah,
Is there anything else for today?
nothing else. We can find the myself, right?
Yeah, okay. Thank you, ma'am. If there are any doubts, you can ask tomorrow or else you can ask me.
Yeah. Okay. Thank you, all of you.